Hi everyone. So let's talk for a few minutes about poles, because that's something that a few people are still a bit confused about, and certainly something we're going to be using a lot. So just to recap, if we've got a transfer function we derived from a linear time invariant differential equation, we can write that as a ratio of two polynomials, the numerator polynomial and the denominator polynomial, and then we can factor each of those polynomials. And the roots of the numerator polynomial are the zeros. So if s equals, say, z1 or z2, then this evaluates as 0, and the whole thing goes to 0. That's why we call them zeros. Whereas for poles, if s evaluates as p1, p2, so on, up to pn, then we've got to divide by 0. So the whole thing blows up. So that's where the name poles comes from. And as I mentioned before, the effect of zeros on our system response is a little bit subtle, and we're going to talk a bit more about that in coming weeks. But poles, it's really obvious. Poles tell us a lot about how the system responds. In particular, if we look at the step response, we often think about the step response as being the transient response and the steady state response. So the steady state response is what we spoke about last week. We use the final value theorem to evaluate where this C final is on this graph. Where do you end up in response to a step input? Or we also looked at ramp inputs and parabolic inputs. The transient response is how you get there. So do you get there quickly or slowly? Is there a lot of overshoot? So we might have a situation where the system, let's say, shoots up very far before it comes down, or doesn't overshoot much at all. The poles tell us that. They also give us a lot of information about the settling time, the rise time, and other times. So the rise time is the time to go from about 10% to about 90% of the final value, and the settling time is the time it takes to get within plus or minus 2% and stay there forever. And you can do settling times for other values, but we're using 2%. So poles tell us all of this transient response information. So how does that work? Well, let's think about, first of all, for the case of first order systems and systems which can be broken down into first order components with real roots. So if all of these p1 to pn are real numbers, then we can do a partial fraction expansion and get our response. So let's look at the response to a step input. There we're going to have y of s equals g of s times u of s. And if u of s is a step input, that's g of s times 1 over s. And then we can write a partial fraction expansion. And let's say we write that down as a over s minus p1 plus b over s minus p2, and so on, until we get to, let's say, maybe it goes up to g over s minus pn. And then we've got also, as well as the poles of the transfer function, we've got the 1 over s. So let's say we've got h over s. And then if we do the inverse Laplace transform to compute the time response, if all of these poles are real, we get a times e to the p1t plus b times e to the p2t, and so on. And then this response here is just the steady state response. So h tells us our steady state response, and we worked out how to compute that quickly and easily from the transfer function last week. And the rest of all of these tell us our transient response, as long as the system is stable. And the point is, if we were going to go through and compute exactly the time domain solution of this, we'd have to go through and compute all the a's and b's and so on. But often as engineers, we don't particularly care exactly what the time domain response is. We just care, is it stable? Does it get to a good final value? And does it get there quickly? And so actually we don't really need to compute the a's and b's and so on. What we need is the p1, p2 and so on. And here we can say the system is stable if all of the p1s are negative. So if all of the poles are negative, then all of these exponentials are decaying. So they're all something that looks like a decaying exponential. And if P1 is bigger in magnitude and negative, it's going to be something which decays faster. And if it's smaller in magnitude, so closer to 0, it's going to be something which decays slower. So what we can do is we can plot the value of these poles on the complex domain. So this is the S on the S plane. And here we're just talking about real poles, and we draw the poles we draw with an X. So if our system is stable, all of them are going to be negative. So they're all going to be over here somewhere. If we have any which are over here in the right half plane, let's say if we have one here, then we get an unstable response. We get something like e to the plus 5t, or something like that. And that means some pressures or temperatures or something like that are blowing up. Now, furthermore, if we have just a first order system, so let's look at the special case of just a first order system, then we can write that, maybe we write that as the form B over S plus A. And so here we have just P1 equals minus A. We just have this first term here. Then we can say that the settling time of this is 4 over A. So that's a nice special case where we can easily compute the settling time. And we can see, of course, that the settling time decreases as A is bigger, which means the pole gets further to the left. So larger in magnitude, but negative. So for first order systems, or systems with all real poles, we want them all to be in the left half plane, and the system converges quicker if they're further to the left. So if these poles are negative in, have negative sign, but are large in magnitude. So you could simply say, if you want to see how well this system responds, first of all, you'll check, does it get to the right final value? And we showed how to do that in last week's lecture. And then you'll just check, are all of the poles negative? And are they far enough to the left that we're going to get a quick enough response? And this kind of 4 over A gives you some idea of what is quick enough. Okay, so now let's talk about the case when some of these poles are going to be complex. So they've got both real and imaginary components. Now, in that case, you could still split it up in terms of the individual complex poles and expand the solution in terms of complex exponentials, but it's actually easier to understand what's happening if we keep the second order terms. So if we keep terms of the form something like PS plus Q over, let's say, S squared plus A1S plus A0. So when you do your partial fraction expansion, you can expand in terms of this form. And again, if we wanted to compute precisely what the time domain solution looks like, we could compute these values P and Q. But actually, in order to get, let's say, a quick idea of whether the system is good or bad, what we really want to know is what are the poles and what do they tell us about the time response. And so what we're going to do, we're not going to look in terms of these A0 and A1. We're going to look at a couple of different ways of representing this denominator polynomial, which tell us a couple of different things. First of all, we're going to look at this in the same way you would approach this, let's say, if you're completing the square to try to compute solutions of this. So let's write this in the following form. Let's write PS plus Q over S plus sigma all squared plus omega squared. So first let's think about what sigma and omega are, and we'll see that they're going to be related to the real and imaginary components of the poles. So the poles are the values of S for which this denominator equals 0. So that's going to be when S plus sigma all squared equals minus omega squared. And so that means that S plus sigma equals, taking square root of both sides, we've got the square root of minus 1 is j plus or minus j times omega, or in other words, when S equals minus sigma plus or minus j omega. So if we're sketching our pole locations here, when we've written the denominator polynomial in this form, then we draw two crosses here, and this point here is going to be minus sigma, and this point here is going to be omega. Right? So that's the real and imaginary components of our pole locations. Now we saw with first order systems that just looking at how far to the left the poles were told us about how quick the time response was. We're going to see something similar here, but we're also going to see that where they are in the imaginary direction also tells us some interesting things about the system response. Okay, so how are we going to do that? We're going to look at this expression here, and then we're going to have a look at our Laplace transform tables, okay? So if we look at these tables, we're going to look for something that looks like it's going to help us. Now, we actually need to use a combination of two rules here, or three. We could say we're going to use the rules for the trigonometric terms here. So let's say omega over s squared plus omega squared. The inverse Laplace transform of that is sine of omega t, and s over s squared plus omega squared, the inverse Laplace transform of that is cosine of omega t. Again, the ut here is just something which is 0 before t equals 0 and 1 afterwards, so we can ignore that since we're just looking at what happens after t equals 0. But that's not exactly the form that we see, right? We have here not s plus omega squared, but s plus sigma all squared plus omega squared, right? So this form here is not exactly the same as this form or this form. But if we see something like s plus sigma in brackets and then all squared, and we see, well, I wish we just had s there, what we can do is we can look at the frequency shift theorem, and that actually tells us how to transform such things. So if I have now f of s plus a, then the inverse Laplace transform of that is going to be e to the minus at times f of t. So what would be the inverse Laplace transform here if it was just f of s? So it allows us to convert from something that has the form f of s plus a to something that has the form just f of s. And so here, if we think replacing s with s plus a, we're going to get it with sigma instead of a, we're going to get this kind of form. So I'm going to, let's just take the part where we just have a real term here. So here the q, let's just say q equals omega. If q is not equal to omega, we can just have some constant out the front. So we've got a real term on the numerator, and we're going to look at a sine wave. We can also have the term with just s on the numerator, and then we look at the cosine term as well, so we can treat those separately. So if we look at this, we've got now omega over s plus sigma all squared plus omega squared, and the inverse Laplace transform of that, say L inverse of that, is going to be equal to, well, we can say it's going to be the product of e to the minus at, but our a is sigma, so it's e to the minus sigma t, times whatever the Laplace transform would have been if we just wrote the time inverse Laplace transform would have been of f of s without this shift in frequency, this f of s plus a. And so in our case, if we just had f of s here, we would have s squared plus omega squared, and the inverse Laplace transform of that is sine omega t. So this is going to be sine omega t. So this is how you use the combination of the rules for sine and cosine and the frequency shift theorem to get the response of this kind of damped sinusoidal response. And what we can see here is that the real part of the pole locations relates to the exponential rate of decay or growth, hopefully decay, because we want the system to be stable, whereas the imaginary part of the pole locations corresponds to the frequency of oscillation. So if we think about what this is going to look like on a plot, if sigma is positive, which means this e to the minus sigma t is decaying, then what we can draw is kind of what we call an exponential envelope. So these graphs here, this is e to the minus sigma t, and this is minus e to the minus sigma t, because that's multiplying sine of omega t. So sine of omega t on itself just oscillates between plus or minus 1, but when we multiply it by e to the minus sigma t, we get something like this. And so we can see that if sigma is larger in magnitude, we're going to get a faster decay on the exponential, and so a faster settling time of our system, because this oscillatory component will go to 0. Whereas if sigma is smaller in magnitude, but still positive, so the overall exponent is negative, we're going to get a slower decay and slower time response. If sigma is negative, and so the overall exponent here is positive, we're going to get exponential growth, and the thing's going to blow up. In fact, if we just have a second order system, and we want to know what the settling time is, then we can use the approximate formula. Settling time is approximately equal to 4 over sigma. So this is very, very similar to the formula that we saw for first order systems. We have 4 over a, where a is the negative of the pole location. And here sigma is the negative of the real part of the pole location, and we still get 4 over that. Now, why is that not an exact expression for the settling time? Because that's actually when these dotted exponential envelopes go within plus or minus 2%. The actual oscillating curve passes in between them. It might cross over at a slightly different time, but it's going to be pretty similar. Okay, so we could stop here. We can expand out our system response. We've got a partial fraction expansion in terms of first order terms, and we get these real decaying exponentials, and then second order terms, and for each one, with either the q, we get the sine wave component, or the p, we get the cosine component. But either way, it's really the sigma and the omega that tell us. The sigma tells us how fast it's decaying, the omega tells us how quickly it's oscillating. We could stop here and we actually get a complete description of our system response. But there's another representation of this second order system which is very widely used, and that's because it allows us to tell a couple of other things about the system response very easily. So let's write a slightly different form. It's going to be the same second order term, but written in a different way. So now let's write a system. Let's consider just a second order system here, where we can write it in this form. C infinity times omega n squared over s squared plus 2 zeta omega n plus times s, sorry, plus omega n squared. Okay, so why do we do this? First of all, I guess we can say, the main thing is to say is that each of these components, omega n, zeta, and c infinity, tell us something about our system response. So we can do this for the second order terms in a higher order system, second order components. But if we look at the case where our system itself is just second order, then it becomes really simple. So what did we say was the final value of a system with a step input? Remember, it was just g of 0, right? So in this case, we have g of 0 equals c infinity, and then substituting 0 for s here and s here, times omega n squared over omega n squared, which just equals c infinity. So that explains the term c infinity. That's the final value. Okay. Now, what about the denominator polynomial? Well, so we're going to have here, if we relate this to the previous representation, s squared plus 2 zeta omega n, s plus omega n squared has to equal s plus sigma all squared plus omega. Now I'm going to call this omega d now. So this was the omega on the previous slide, and omega d here is going to stand for damped frequency, and this is going to stand for natural frequency. Now if we expand this out, we get s squared plus 2 sigma s plus sigma squared plus omega d squared. And so we can clearly see here, just by matching terms, we have sigma equals zeta times omega n. And by matching the constant term, so we have the constant is this combination here, and that should equal omega n squared. So we can now, let's rearrange this a little bit, we can write omega d squared equals omega n squared minus sigma squared. And now if we substitute in for sigma squared is going to be equal to zeta squared times omega n squared, we can pull out the omega n squared, and we've got 1 minus zeta squared. And then we can take the square root here, and we just write omega d equals omega n times square root of 1 minus zeta squared. Okay, so let's think about what this means in terms of pole locations. So if we're drawing two poles on the S-plane here, remember we've got here minus sigma is the real part, and this is omega. Now we'll write omega d, which was just omega in the previous slide. So if we have omega d here and sigma here, then let's say the magnitude of this vector is going to be the square root of omega d squared plus sigma squared. But that's exactly what omega n is, right? So we've got omega n squared equals sigma squared plus omega d squared. So this magnitude here is actually omega n. And it turns out, if you do a little bit of trigonometry, that this angle here, this angle is the inverse sine of zeta. So we can think of our representation from the previous slide we thought of as the Cartesian coordinates, the real and the complex, real and imaginary components of a complex number. Now we've got omega n is the magnitude of the vector, and zeta is kind of the angle. Actually, sine inverse of zeta is the angle. But so now we've got the same complex number written in polar coordinates. And so why would we want to do that? Well, we can take any complex number, we can write it in Cartesian or polar coordinates. The use of the Cartesian coordinates was the real part told us the settling time of the system. It turns out, and I'm not going to derive this here, but you can see in the book where it comes from, or in the lecture slides from lecture 3. Turns out that this polar coordinates tells us something about other parts in the time response. So actually, TR, the rise time, is approximately equal to 1.8 over omega n. So this absolute value here tells us about the rise time. And what about the angle, and what about zeta? Well, I'm not going to go into all the details here, but it turns out that the formula for percentage overshoot, so how much does the step response go past the final value before it comes back, depends entirely on zeta. In particular, now this formula, you don't need to remember this, it's given on your formula sheets in the final exam. There's a relationship between percentage overshoot and zeta, or you can go back the other way for a particular percentage overshoot, what should zeta be? And we can actually plot that. So the horizontal axis here is zeta, the vertical axis is percentage overshoot. And for a few key values, often we might be looking for a 5 or 10% overshoot. And we can see that that corresponds to a zeta of 0.7 or 0.6. So I guess you could say that, let's say the point is basically that percentage overshoot is, let's say, a function of zeta. And for commonly used percentage overshoots, we can say what the zeta should be. So basically, to summarize, we can say that by looking at the Cartesian coordinates of this complex pole pair, we can tell what the oscillation frequency is and what the settling time of a second order system will be. And from the polar coordinates, we can tell what the rise time and the percentage overshoot will be. So if we think about all the things that we want to know about our system, we know what the final value theorem is, final value is from the final value theorem. We've got rise time, we've got settling time, we've got percentage overshoot. So that's for a single second order system component. If we have a system which expands out into multiple first and second order components, the formulas for rise and settling time and so on aren't exactly correct anymore, but they're still going to give you a very good idea of how quickly the system responds and whether it's oscillating a lot. So by looking at if we look at a pole zero diagram and we see all the poles are, let's say, far to the left, and they don't have, if this zeta here, if the system is well damped, so it's going to have low overshoot. It means this angle here is quite big, so you want poles kind of close to the real axis and far out to the left. Okay, so that's kind of a whirlwind tour of poles and why they're important for control system analysis and design.